Hey, Carlos, you want to pull that door shut?
Yes, sir.
Thank you. Okay, so last time we talked about, or finished, evanescent waves, and we saw how they lead to frustrated total internal reflection, or tunneling. We looked at a bunch of devices that are based on frustrated total internal reflection, including some that we did. And then we got started, or I guess we talked about Brewster's angle. And then we got started with interference, and in particular, two-beam interference. And then we got homework due on Thursday. So, any questions? We're good? Okay. All right, so we'll get back into the two-beam interference. And to recap, we've got this situation where we have two plane waves. And so we're in the electromagnetic model. And the wave vector for plane wave 1 we can write as the wave number times the unit vector u1 hat, and the wave vector for beam 2 is the same wave vector or wave number, but different unit vector direction in general. We haven't said anything about polarization, and what we want to know is power flow. Power flow means that we've got to worry about the Poynting vector, so let's talk about the complex Poynting vector, which is 1/2 the complex amplitude vector of the electric field crossed into the complex conjugate of the complex amplitude vector of the magnetic field. And since we've got two waves here, just to be explicit, then this has got to be the complex amplitude vector for the total electric field, and likewise the total magnetic field. And so our whole job is to find these complex amplitude vectors, put them in here, work out what the complex Poynting vector is, and from that we can calculate irradiance in any plane or any surface. So we were kind of in the middle of that. And to begin with, we always have to be able to write down the fields. And so we wrote down these two fields as the complex representation for the first field is a complex amplitude vector times e to the j omega t. And then this complex amplitude vector, we said let's just represent it as E1, drop the explicit spatial dependence as we always do. And then because this is a plane wave, we can write it as having an amplitude and having a phase. And then it's going to have some polarization state, so P1 hat. And then this is going to be an e to the minus j k1 dot r. And I guess what we did, now that I look at my notes, I guess what we did is we said, all of this stuff, let's just write it as a constant vector, complex vector E10. So E10 has the magnitude, phase, and the polarization state in it. And same thing for E2, exact same expressions, except just subscripting with a 2. So we'll just write E2 as E20 vector, e to the minus j k1, or rather k2 dot r. And then we said that the total complex representation, or the complex representation of the total field is just the sum of the complex representations of two fields. And And then we plugged these in, found that this was E total, e to the j omega t, where E total was just E1 plus E2. So the complex amplitude vector of the total field is just the sum of the individual complex amplitude vectors, which is kind of intuitively obvious. Okay, so then we were trying to write down the magnetic field, and I'll just write it down here. So we went back to the Maxwell equations to, what was it? Yeah, Faraday's law. And after plugging in, what we ended up with is that H total is equal to 1 over the impedance of whatever medium we're propagating in times U1 hat cross E1 plus U2 hat cross E2. Okay, so we've got the two things that we need in order to calculate the complex Poynting vector. So let's put those in and see what works out. So we have the complex Poynting vector is going to be 1 over 2 times E1 plus E2 crossed into 1 over eta, and then we have U1 hat cross E1 plus U2 hat cross E2, and then this is all complex conjugate, and the unit vectors are not complex, so the only thing that gets complex conjugated are these complex amplitude vectors.
So when we say E total, we're ignoring the e to the j omega t, so we don't need that for the complex.
Well, see, here's the e to the j omega t. This is the complex amplitude vector of the total complex representation of the field.
Okay.
And so that complex representation for a monochromatic wave, and a plane wave is a monochromatic wave, we can always write the time dependence here, and then everything else has the spatial dependence, and that's the complex amplitude vector.
Oh, and that's all we need. We don't need the time dependence for that.
Yeah, because this, remember, I keep saying this is the complex Poynting vector. And the definition of the complex Poynting vector is what? This gets back to that advice at the beginning of the semester. You've got to really pay attention to definitions and terminology. And here's a crucial definition. Complex Poynting vector is 1/2 the complex amplitude vector of the electric field crossed into complex amplitude vector of the magnetic field, complex conjugate. And complex amplitude vectors are the pieces that don't include the e to j omega t. So that's the crucial definition. So I'm glad you asked that, Carlos.
So when we talk about the time average Poynting vector, do we just include the time?
Nope. So the time average Poynting vector, oops, wrong, is the instantaneous, let's see, I forgot how to write that. Yeah, it goes something like that. Script S. That looks like a B, doesn't it? Okay. I don't know. We'll do that. That's our script S. So the time average of the instantaneous Poynting vector is the real part of the complex Poynting vector. So the beautiful thing is once you have the complex Poynting vector, you've got everything. If you need the time average, just take the real part. Done. Okay, so now we need to play around with this thing and get it in a form that we can extract some meaning from. So, we have 1 over 2 times eta out in front, and then we're gonna have a bunch of terms. So let's take E1 here, it's gonna be crossed into the first term there, so we have E1 crossed into U1 hat crossed into E1 complex conjugate. And then let's take the E2 and the second term there. So we have E2 crossed into U2 hat, crossed into E2 complex conjugate. And then let's take the E2 crossed into the first term. So we have E2 crossed into U1 hat cross E1 complex conjugate. And then finally, the last term is E1 crossed into that, so we have E1 crossed into U2 hat cross E2 complex conjugate. And close curly braces. So,
Is there a plus between the first line and second?
oh, thank you very much, perfect, yep, you're right. Okay, fine. Now, we can make use of the back cab rule. So, we have that A, vector A crossed into the cross product of vector B times C is equal to B, A dot C, minus C, A dot B. Y'all remember that one? Of course. Yeah, okay. So let's apply that. Which means we've got 4 terms here. So how many terms are we going to end up with?
8.
8. Okay. That sounds like fun. Let's go ahead and do it. So we have 1 over 2 times eta, curly braces. Then we have, for this first one, B is U1 hat, and then it's multiplying, yeah, E1 dotted into E complex conjugate. Oh, we know what that is. Well, magnitude squared of E1. And then we have minus E2 complex conjugate, and we have U1 hat dotted into E1. What's U1 hat dotted into E1?
Shouldn't that be E1 complex conjugate?
Yes, thank you. Perfect. So what's this dot product? U1 hat dotted into E1?
Should be E1 itself.
Has to be 0, why?
Because it's orthogonal. Or,
Yeah, the electric field is orthogonal to its direction of propagation.
Oh, that's right.
So that's 0. Okay, well that was easy. Okay, and then let's do the next one here. So we have U2 hat, and then looks like we've got magnitude squared of E2. Okay, that's nice. Minus E2 complex conjugate U2 hat dotted into E2. And oh gee, what's that? 0, 5. Okay, great. Then we've got this one. So that's U1 hat. And now we've got E2 dotted into E1 complex conjugate minus E1 complex conjugate. And we've got U1 hat dotted into E2. Can we say anything about that dot product? Nope. Because in general, they're not in the same direction. So that won't be 0. Okay, and then we've got the final one over here. So we have U2 hat, E1 dotted into E2, complex conjugate, minus E2 complex conjugate. And then we've got U2 hat dotted into E1. And again, we can't really say anything about that dot product because these are in general in different directions. So it looks like out of 8 possible terms, we're really left with 6 terms. Okay. All right. So, can we say anything further about those 6 terms?
Combine the U-hats in some way?
Yeah, maybe. But there's nothing really that jumps out at us, is there? So, okay. So I guess that's about as good as we can do. But the beautiful thing is that if we were to take the real part of this, we know that's going to be the time average Poynting vector, and therefore we can get the time average power flow. Okay, at this point, let's do the following. Let's look at a special case. And that special case is when we have collinear beams. So U1 hat is parallel to U2 hat. And you're going to be surprised how many cases come down to collinear beams as we go through the rest of the semester. A lot of devices end up giving you collinear, co-propagating beams. So even though we label this a special case, it has very broad application because lots of useful devices boil down to this situation. So if I go back now to this expression and look at what happens when these are parallel, which is the same thing as saying U1 hat is U2 hat and vice versa, then notice that now goes away. And that goes away. Well, that's nice. So I'm just left with these 4 terms, and notice U1 hat, U2 hat, U1 hat, U2 hat, they're all the same. So I can write down that this is U1 hat 1 over 2 times eta, and then notice, well, let's just write it down. Okay, so we have E1 magnitude squared plus E2 magnitude squared plus we've got E1 dotted into E2 complex conjugate plus E1 complex conjugate dotted into E2. Does this thing look familiar? One term is the complex conjugate of the other term. If we add something plus its complex conjugate together,
What's real?
we get the real part. So this is just 2 times the real part of E1 dotted into E2 complex conjugate. So interestingly, our complex Poynting vector, every term is now real. Okay, we're not going to worry too much about that. Let's do the following. Let's say we want to calculate the irradiance. And we want to calculate the irradiance in a plane that's perpendicular to U hat, U1 hat, whatever we want to call it. Perpendicular to the direction of propagation. So that means that the surface normal of that plane is the same as U1 hat, right? So the irradiance, what's our expression for the irradiance?
Magnitude
Across any surface? In terms of the complex pointing vector?
The one over 2 eta times.
That's in terms of the electric field. But in terms of the complex pointing vector. What's that? No. Yes, that's why I'm asking. We take the complex pointing vector, we dot it into the surface normal of the surface over which we want to calculate the irradiance. We take the real part. And then we take the magnitude, just so we don't have negative irradiances. Which is the same thing as saying we're throwing away the information as to whether our surface normal is in the direction of propagation or opposite to the direction of propagation. Okay, so if we take n hat and dot it into this complex pointing vector, all we do is have n hat dotted into u1 hat, which is 1. So that's no big deal. What's that?
Sorry, I was just saying, so it's just the real part of the pointing vector.
Yeah, and we already noted everything's already real. And magnitude, well, this is going to be positive. So that leaves us with E1 magnitude squared over 2 times eta plus E2 magnitude squared over 2 times eta plus 1 over 2 times eta E1 dot E2 complex conjugate plus E1 complex conjugate dot E2. Okay, what's this right here? That first term.
Radius.
Just the irradiance. The irradiance of the first beam. And so the second term is just the irradiance of the second beam. So what's the third term? It's the interference term. Let's just give it some name. Call it J12. Doesn't matter. So this is the interference term. So notice what we just said. That if we have two beams propagating in the same direction, that the irradiance is the sum of the individual irradiances plus an interference term. Always. That's how it works out. Okay. So, okay. So to calculate I1, what do we need to know?
Just the E field first.
Yeah, all we need is E1. What's E1? The complex amplitude vector of the first field. Likewise, and so is I1 difficult to calculate? It's trivial. Likewise, I2 is trivial if you know the fields. And you pretty much always know the fields. So the first thing that you do in an interference problem, well, we'll get to step 0 in a minute, but the first step is write down the fields. Always. I suppose you first draw a diagram, but you've got to be able to write down the fields. Once you write down the fields, then the first two terms are trivial to calculate. It's no big deal. And so the second thing that you do is, knowing those fields, calculate I1 and I2, which are trivial, and also calculate J12, which is what we're about to do. Calculate the interference term. And once you have those three terms, you're done. And you've got the irradiance, so you know what the interference is. And that all falls out of complex pointing vector, as it should. Okay, any questions?
Is this interference term, is that in general always negative?
Nope. It is not. So this is the interference term.
Yeah.
And what we want to do now is some examples to explore what that means. And it turns out what it means is pretty simple. But there's some important things that fall out of that analysis. In fact, the crucial things. So that's where we want to do some examples to get a feel for it.
So, I guess, how does this satisfy conservation of energy, I guess?
Yeah, that's one thing I want you to focus on, but I'm not going to tell you how until we do some more examples after the first examples. So, but I want you to think about that. How does it satisfy conservation of energy? Because if you, well, and of course it always will, but there are some things you've just got to take into consideration in order to understand how that works out. So first of all, let's do an example. Let's say we have, we're going to be talking about collinearly propagating beams. So let's say we have 2 plane waves, and the directions of propagation, let's say, are in the z-hat direction, which is no great assumption. We don't lose any generality because we can always rotate our coordinate system, so that's true. And let's say that both have linear polarization in the x direction. So if I draw a little picture, then that's the z direction, x direction, and y is out of the board. Basically, I have k1 in the z direction, and I have e1 in the x direction. And likewise, the other way, k2 is in the z direction, and e2 is in the x direction. And what I want to know is, in a plane perpendicular to z, what is the irradiance? So what's the first thing we do? Right on our field. So tell me, what is E1?
The magnitude times x hat e to the j omega t.
So it's got a magnitude, call it E10. What else does it have?
Direction x hat.
Yeah, polarization, x hat, okay.
E to the minus j k1 and then z.
So e to the minus j k1z. And let's let, because these are in the same directions, then k1 is going to be k2, so let's just call it k, just to keep our notation simpler. So we have, and that's going to be wave number times z hat. So when we take k dot r, that's going to give us the wave number times z. Okay? All right, what else do we have? Polarization, magnitude,
Frequency.
spatially dependent term. Pardon?
E to the jt.
Yeah, it also has, in general, a phase. Let's call it T1. So E to the J T1. Okay, so was that hard to write down the field?
A little bit.
A little bit. But soon, it should become second nature to you. Because E1 is what part of the field?
Complex amplitude.
Complex amplitude of
Complex amplitude vector, this nonsensical name we made up. Okay, complex amplitude vector, which is the piece that multiplies e to the j omega t in our full complex representation of the field. And if we want the real representation, what do? take the real part of the complex representation. Always, that's how you go back and forth. Okay, so E1 over there is just the complex amplitude vector of the complex representation. Okay, and that complex amplitude vector, what information does it have?
Polarization.
Polarization, magnitude, phase, and the spatially dependent part. Always. Okay, so E2, we write it down, it's got the same polarization, it has some magnitude, E2 0 has some phase, V2, same spatial dependence. And at this point we can write down the irradiance. So that's just going to be magnitude squared of this thing, which is E10 magnitude squared. If we say that's always positive real, we don't even need the magnitude squared there. Over 2 times eta. And I2 is going to be E20 squared over 2 times eta. And so what we really need, I mean, the only thing that poses any challenge whatsoever to calculate is the interference term. That's really no challenge because all it is this. So we have E1 dotted into the complex conjugate of E2. X hat dotted at X hat is 1. And then we have E1, 0. And then we've got that E2, 0. And so, and this whole thing is complex conjugated, right? But is E2 0 complex?
No.
No, because it's the magnitude. By definition, it's real. So we have E1 0, E2 0, and then we have e to the j phi1 times e to the j, or complex conjugate of e to the j phi2. So it's e to the j phi1 minus phi2. Okay. And this times complex conjugate of that is 1. Okay, so that's our first term. And then we have E1 complex conjugate dotted into E2. So X hat dotted into X hat is 1. We've got E1 0, E2 0.
Phi2 minus C1.
Minus J, Phi1 minus 2. I'll just write it this way, with the minus sign up front rather than in there. And then we're done. That's it, right? And so I can pull out, I did forget one thing. The 1 over 2 times eta, right? So I have 1 over 2 times eta. I can pull out the E10, E20, and then I have e to the j, let's just call this delta phi, all right? So delta phi is phi1 minus phi2. So e to the j delta phi plus e to the minus j delta phi, and we recognize that as cosine. So we pull the 1/2 in over here to get the cosine. So we have 1 over eta, E10, E20, cosine of delta phi. All right, and then we're not quite done. Here we have I1 and I2. Notice the square root of I1, square root of I2, and compare it to this. And we see that that is 2 times the square root, I1, I2, cosine of delta phi. So that's our interference term. So the full irradiance is I1 plus I2 plus 2 times the square root, I1, I2, cosine of delta phi. That's the irradiance that we get in a plane perpendicular to the direction of propagation, which is the sum of the individual irradiances plus this interference term. And that interference term has a distinctive functional relationship to the irradiances, to square root of I1, I2, and then the phase, cosine of delta phase, the phase difference. So when you look at this and ask, well, what's interesting? It's always the interference term that's interesting. And in the interference term, what is critical? Well, it's got two pieces. It's got the product of these square roots, and it's got the phase term. And the phase term is almost always where the action is. When you're doing interference problems, that's the key thing, the phase difference. Okay, so let's probably play around with this a little bit. Notice that if delta phi was equal to an integer times 2 pi, so this would be 0 plus or minus 2 pi, plus or minus 4 pi, etc. Then the irradiance is I1 plus I2 plus 2 times the square root I1, I2. So the interference term is positive. It adds to the sum of the individual radiances.
Excuse me, this is the meaning of constructive and destructive.
That's where we're going. Yes. Yes, okay, so let's label it. We call this constructive interference. So the interference term is adding to the sum of the irradiances. On the other hand, if delta phi is equal to m plus 1 times 2 pi, so that would be plus or minus, no, m plus 1 times pi, there we go. So it would be plus or minus pi, plus or minus 3 pi, etc. Then the irradiance is I1 plus I2 minus 2 times the square root of I1, I2, and we call that destructive interference. So the total irradiance is less than the sum of the individual irradiances. I remember we talked briefly about how we want to pay attention to energy conservation.
Yeah.
So at first glance, it looks like here we've got more irradiance than what we started with, and here it looks like we have less. And so the question is, well, where did the other power go? We'll answer that later. Okay, first of all, though, we want to look at the case of I1 equal to I2. Then we go up here, I1's equal to I2, so we get the square root of I1 squared, basically. And we've got 2I1 there, so we can pull a 2I1 out. So I is equal to 2I1, 1 plus cosine of delta phi. And we can use a half angle formula and write that as 4 times I1 cosine squared delta phi over 2. And so if I plot this then as a function of delta phi, and here's the irradiance, basically what ends up happening is I get something like this, and we have that this is 4 times the irradiance of an individual beam. And actually I drew this wrong, but I'm not going to worry about it. It's close enough. Close enough for our purposes. Okay. So this interference term then for collinearly propagating beams is just 2 times the product of the square root of the individual intensities times cosine of the phase difference. And by playing with the phase difference, you can get wildly different irradiances. All the way from 0 to 4 times an individual irradiance if the two irradiances are the same. Yeah.
When you label the constructive and destructive interferences up there, is it more proper to say like fully constructive interference?
Yes.
And fully destructive?
Correct.
Okay. Like as much as it can be.
Mhm. Yes.
Based on the amplitudes of the wave.
Yeah, that would be a more accurate way to label it. In practice, when people talk about constructive and destructive interference, usually they're talking about the maximum and minimum. But, yeah, so. Okay. Are we good with this example? See how it works out? So it's always, I like to draw things out just to make it clear. But then it's write down the fields, calculate I1, I2, and J12, add them together, and then just see what it means. That's it. Okay, so let's do another example. In fact, let's go over here. Okay, so in the next example, I'm just going to draw the situation now, since hopefully we're kind of used to diagrams. Let's say that the first incident beam is exactly the same, no difference. And let's say that the second incident beam is linearly polarized, but in the y direction. So, first thing we do is write down the fields. Okay, we already wrote down E1 over there, so all we really have to do is write down E2. So what's E2?
Y hat.
Y hat, polarization, amplitude, phase, spatially dependent part. Okay, so the only difference from what we have over here is the polarization, y hat. Okay, so I1, is it going to be any different? No, obviously not. I2, is it any different? No. How about J12? E1 dotted into E2 complex conjugate, what does that give me?
0.
Right? And the other term, what does it give me? So we have a big fat 0. So the irradiance is the sum of the individual irradiances. The interference term is 0. Why? Because we have two orthogonal polarization states. Moral of the story, orthogonal polarization states do not interfere. Makes life very simple. So you cannot have interference with orthogonal polarization states. Now, later, I'm going to show you how you can force interference between orthogonal polarization states. But if you don't do anything, there is no interference between orthogonal polarization states. Okay, let's do another example. Let's say that I have the first beam. Let's say that it is circularly polarized. And let's do circular polarization on the clockwise orientation. So we'll say clockwise circularly polarized light for the first beam. And for the second beam, let's say it's also clockwise circularly polarized. Okay, first thing, we need to write down the field meaning the complex amplitude vectors for the field. So E1 is gonna be what? What's the polarization state? Yeah, what's clockwise circular polarization?
So we have a vector now, or,
Yeah, I mean, just like we had a vector here.
oh,
Yeah.
one J. or
One
something.
J.
Yeah,
Oh,
and
my
we
gosh.
should, let's normalize it, so
One
our
little two.
amplitude is not ambiguous, and let's just use the Jones vector. So we don't have to bother writing out the components. Okay, and then I'll have an amplitude, E1, 0, and the amplitude is the amplitude because the Jones vector is normalized. And then phase, e to the j phi1, spatially dependent part, e minus j k z. And E2 is the same thing, except subscript by 2 instead of 1. So E2, 0, e to the j phi2, e to the minus j k z. And then the irradiance is what? The irradiance for beam 1.
It's still one zero square has to go over 4.
E1 0 squared over
By
2
two.
times eta.
Yeah.
Because this dotted into its complex conjugate is 1. So same result as when we did it over here just for x hat. No difference. Are we all good with that? Okay. All right. So I2, do the same thing. E2, 0, magnitude, or squared over 2 times eta. So what about J12, the interference term?
Sorry, shouldn't we 1/4 because we have 1/2 in the definition and 1/2 in
So, yeah, we have 1/2 time, or 1 over root 2 times 1 over root 2 is 1/2. And then 1 times 1
Okay.
plus, yeah, j
Yeah.
times minus j, yes. Okay, so J12, we've got E1 dotted into complex conjugate of E2. So this dotted into the complex conjugate, we already said is 1. And then we end up with E10, E20. So E10, E20. And we end up with EJ phi1 minus phi2 e to the minus jkz times this complex conjugate is just 1. Okay, so that takes care of my first term. Second term, I get E10, E20, e to the minus j phi1 minus phi2. And hey, that sure looks familiar. In fact, it looks exactly the same as over there. So that's just 2 times square root I1, I2 cosine of delta phi. What's going on? Why is it the same? So what I have over here, yeah, for both. So in other words, over here I'm interfering 2 beams having the same polarization. What am I doing over here?
same polarization.
Same polarization, which gives me the same result. But it doesn't matter what the polarization state is, if it's the same, I always get this result. So everything we just said over there still pertains. Okay, let's do another example. Let's say that, oops, see. Let's say that the first beam is again clockwise circularly polarized, but the second beam is counterclockwise circularly polarized. So again, we write down the fields. E1 is the same as right here. What's E2?
Same thing, but minus j.
Yeah.
Yeah, same thing but a minus j, so 1 over root 2, 1 minus j, E2, 0, e to the j phi 2, e to the minus j k z. Okay, so I1, is it any different? No, obviously not. I2, is it any different? No, same thing. So calculate J12. So I have E1 dotted into E2 complex conjugate. So I've got this dotted into the complex conjugate of that. What does that give me? 0. And then E1 complex conjugate dotted into E2 gives me another big fat 0. Interference term is 0. Total irradiance is just the sum of the individual irradiances. Why?
Different polarization.
Orthogonal polarization states. So over here, orthogonal polarization states, when we do the dot product, always gives us a 0. So it doesn't matter what polarization states we have, as long as they're orthogonal, then we get no interference. So what we've seen is that if we have two beams with the same polarization state, we always get the same result. Question?
So it was clockwise and counterclockwise? That's orthogonal?
Yeah, they're orthogonal. You bet.
180?
No. What's our definition of orthogonality? We have some Jones vector, and now so we have some Jones vector dotted into some other Jones vector complex conjugate. If they're orthogonal, they're 0. So take this, dotted into the complex conjugate of that, 0. That is orthogonal. Again, definitions, terminology. Okay, so orthogonal polarization states will never interfere. We believe that? It's a good thing to believe. You can have faith in that. That will always be the case. The only time it's not true is if you do something to force them to interfere, which is a topic for another day.
That will never naturally occur then?
Nope.
That we will do.
No. Oh, yeah, we have to do something very deliberate. Yeah. Yeah, and I'll show you how that pertains to interference contrast microscopy. It can be extremely useful to force that to happen. Okay. So you believe me? How this works? Maybe one final example, just for fun. We have same polarization states, 2 examples. Orthogonal polarization states, 2 examples. What if we have 2 polarization states that are not the same but are not orthogonal? So let's make that our 5th example. So let's just pick some easy ones to work with. Let's say our first is linear polarization in X. And let's say our second beam is linear polarization rotated by beta. So let's look at that in the XY plane. So basically, here's E1, and E2 is rotated at an angle beta. Okay? All right, so E1, we write down that field. Well, it's the same as what we have over there. So we've written it down already. What's E2? What's the polarization state?
Rotated by angle beta.
What's that?
Rotated by angle beta.
Yeah, so tell me the normalized Jones vector for that.
Okay. So cosine minus sine, sine, cosine.
R minus beta.
Yeah, I mean, we could do all that, but in the end, what's the X component of this guy?
Cosine of beta.
Cosine of beta. What's the Y component of that?
Sinus.
There's our polarization state. falls out of everything we did with the Jones vectors.
Would it be fine though to just write it as e to the j beta, just another?
Well, no, because number one, it has to be a vector. It's a polarization state. And e to the j something is a phase term.
Okay.
Because, you know, this, what is it? What's a phase term? It's a spatially dependent phase. This is a constant phase term. Okay? So what else do I need? Yeah, magnitude, e to 0, what else?
E to the
A phase, e to the j phi 2, what else?
E to the minus j.
E to the minus j kz, the spatially dependent phase. Okay. So I1 is what?
Same one.
How long can we beat that dead horse, right? So it's E10 squared over 2 times eta. I2 is what?
Same as
Yeah, E20 squared over 2 times eta. And then the interesting thing, the interference term. So we have E1 over there dotted into E2 complex conjugate. So the polarization states, when I do that dot product, what do I get?
Oh, just cosine thing?
Just cosine beta, right? Cosine beta. And then I have the rest of it here times the complex conjugate of this stuff. So that gives me E10, E20, e to the j, phi1 minus phi2, plus the next piece. What does the dot product give me? So the E1
Zero.
complex conjugate dot E2,
So it'd be cosine beta.
cosine beta. And the rest of it? From the E1 complex conjugate down into E2?
Same.
Same, but with the negative.
Yeah.
Yeah, so E1 0, E2 0, e to the minus j, phi1 minus phi2. Voila, we have our interference term. So cosine beta is common, we can pull it out. Oh, and I forgot the 1 over 2 times eta, right? So cosine of beta, I can pull it out. E120 is common, I can pull it out. That leaves me with this plus that, which is a cosine when I pull that 1/2 in. So long story short, that gives me 2 times square root of I1, I2, cosine of delta phi, and now I have this extra cosine of beta hanging around. So this first piece just looks like a regular interference term, right? For identical polarization states. What's that cosine beta mean?
It's the orthogonal part of one, or sorry, it's the parallel, how do I say that? It's
It's the component that it interferes with.
It's the part of E2 in the direction of E1. That interferes. The orthogonal part does not interfere. So what fraction of this is in that direction? Well, cosine of beta. That's why we have a cosine beta. Okay, so when we have 2 polarization states that are not orthogonal, but not the same, how much interference do we have? Basically, what fraction of one is in the direction of the other? That is going to multiply our usual interference term. That's it. Okay, any questions? So, do you feel like you can do any tubing interference problem under the sun with collinear beams? Correct answer is yes. Because what do? Step 1? Write down the fields. Step 2?
I go the yes.
Yeah, I1, I2, trivial, J1, 2, now that's trivial too. So what's the hardest part here? Write down the fields. How hard is that? Not.
Not very good.
Not at all. Once you get used to it. I mean, once you understand what information is contained in the field, what part of the field am I talking about? I'm talking about the complex amplitude vector. Why? Because that's what's important for the complex pointing vector. Once you've got that train of concepts, then this stuff, writing down the fields, it's just easy. It's not a big deal. But if you don't have those train of concepts, you'll screw up every which way possible. Why do I know? I've seen it countless times. And I'm sure when I was a student, I did it countless times until I figured out, oh, I have to pay attention to the details. I have to get them straight. I've got to understand the pieces. And once you do, it's all trivial. It's not a big deal. Okay, so we just did all of this for the electromagnetic model. But we have another model we've been dealing with, namely the scalar model. How does all this work in the scalar model? That is the question we want to address now. And when you see it, you're going to say, well, why didn't we do that first? And there's a reason why we didn't do it first. It's too easy.
They were complaining the whole time the other way is too hard.
That's right. That's right. So if I have a plane wave, K1, a plane wave, K2, and I want to know what is the irradiance in some surface here in the region where they overlap, what would I do? What's the first thing I would do? Write down the fields. Okay, so the full complex representation of a plane wave, well, of a monochromatic wave, is a complex amplitude times e to the j omega t, right? And we usually write this complex amplitude, we make the spatial dependence implicit and drop the explicit notation. Okay, and then for a plane wave, u1 is equal to what?
It's just E1, or there's no polarization information in there, right?
Right, it's a scalar wave.
It's just the magnitude, so it's.
Just a magnitude, so let's give it some symbol, I don't know, A1, magnitude. What else do we need to write down? What other information is in this complex amplitude? Phase, okay, so e to the j phi1. What other information is in there? The spatially dependent phase, e to the minus j k1 dot r. Okay. Now, what about the other field? And actually, you know what? Yeah, okay, let's do this. So this is for a plane wave. Just to make this more fun. Let's just hold off on that. Let's write down the other field, the complex representation. So it has a complex amplitude times e to the j omega t. We suppress the explicit spatial dependence. Just write it as U2. What's the total field going to be? The total, let's say total complex representation of the field. So that would be U total of R and T. What's that going to be?
U total R e to the j omega.
U total, okay, let's do it that way, sure. U total R, e to the j omega t, is that what you said?
Yes.
Okay, perfect. Okay, and then what's this thing?
U1 plus E.
Yeah, first of all, let's suppress the explicit spatial dependence just because it's pesky having to write it down. And we all know now it's there even if we don't see it. And so, okay, fine. Another way we could write this is as the sum of the individual complex representations, right? And so if we substitute in, assuming they're monochromatic, which is what we're assuming, then we have u1 e to the j omega t plus u2 e to the j omega t, and that's equal to u1 plus u2 e to the j omega t. And, oh yeah, those have to be equal, right? So the complex amplitude vector for the total field is the sum of the individual complex amplitude vectors, which of course is what we would have expected. That's kind of trivial. Fine. Okay, now in the scalar model, how do we calculate the irradiance? I know I'm taxing your memories.
Just
The
squared.
magnitude squared.
Yeah.
Magnitude squared of?
With A.
So let's say this is the total irradiance. So, well, just in general, the irradiance is magnitude squared of the complex amplitude vector, right? And so in our case, we're looking for the total irradiance, which is going to be the magnitude squared of the complex amplitude vector for the total beam, which is magnitude squared of the sum of the individual complex amplitude vectors, which is u1 plus u2 times u1 plus u2 complex conjugates, right? And so if I work through this, I have magnitude squared of u1 plus magnitude squared of u2 plus u1 u2 complex conjugate plus u1 complex conjugate u2. Hey, that looks familiar.
Real version.
Doesn't it look
Yeah.
just like that, except for the scalar case? So we have the irradiance of beam 1, the irradiance of beam 2, plus some interference term. Wasn't that easy? Okay. But there is a subtlety here that often trips up people, or they don't even notice it. It can nail them. Over what surface is this expression for the irradiance valid? Normal to what?
Whatever's in between the two of them.
Okay, the bisector. And what if this is at 45 degrees, that bisector, and this is at 45 degrees, that bisector? Does it matter?
There's a scalar model.
It's a scalar model, but it turns out it matters a great deal. And this is a point that either people don't think about or they screw up on. When we wrote this down, did I say anything special? Actually, for you guys, I didn't this time. In other semesters, I say it, but then no one appreciates it. So I didn't bother saying it this time. So in the scalar model, this means the irradiance in the plane that's locally perpendicular to the direction of propagation of this. In the scalar model, that's what this is. And here, we've got a little problem. There is no surface here that is locally perpendicular to both directions of propagation. So does this have any meaning? Can I even do this?
Can't you, find the, it depends on where you want to measure, I guess.
the one orthogonal surface onto the other orthogonal, like one.
You
to
could
the
try
max-
something like that.
max of-
You could try something like that, but once you get to that point, really, the only thing you can do is go to the electromagnetic model in order to ensure that you're accurate. So does that mean this has no utility?
So if both of them are parallel, then it does, right?
Yeah. Did I erased it. Remember I started off on this whole thing on the electromagnetic side saying, let's assume collinearly propagating beams. Well, hey, if these are collinear, beautiful, everything works fine here. It turns out it still works fine if they're not collinear, but if they're at most paraxial. What does paraxial mean? It means that angle between them, call it, I don't know, alpha, is small. How small is small? Yeah, it depends. Depends on how accurate you want to be. 1 degree? Sure, no problem. 5 degrees? Yeah, that's probably fine.
You said paraxial?
Paraxial.
Paraxial. Oh, like paraxial approximation.
Exactly. Because in the paraxial approximation, cosine of the angle becomes what?
Just the angle.
Becomes 1. Sine of the angle becomes the angle. But the cosine of the angle becomes 1. And frankly, what's going on here, if I take some plane, at most I'm going to be off by cosine of the angle in terms of the radius. So if I assume paraxial beams, so there's not much angular difference between them, then this works just fine. Up to about maybe 10 degrees, 10 degrees, you're starting to get a few percent error. So, 5 degrees, 2 degrees, 3 degrees, works great. Okay, so all of this is fine if these are paraxial beams. And what plane is this true in? Well, the one you mentioned, Matthew, the one that splits this, that plane, yeah, it's true. But if it's paraxial, it turns out that plane and that plane are identical to that plane, so it doesn't really matter which one we say. Because cosine of that small angle is essentially 1. So it all works out to be the same. Okay.
So all of this gets really nasty when you have different frequencies, right? The two waves are
Yeah, no, it's not. All that happens is you end up with,
different.
so, here, yeah, you end up with a time-dependent term in your interference term. So you end up with a beat frequency. So it's not really that big of a deal. It's a straightforward generalization of what we've already done. We're not going to worry about that. We're always going to assume the same frequency. But it's not that big of a deal. Okay, so now let's get back to this. Plane wave, U1 is this thing, and U2 is going to be the same functional form, just subscripting with 2. And now let's just say that we have propagation in the z direction. So then this just becomes minus kz. So we have collinear propagation. If I go over here, what do I get? Well, I1 is just A1 squared, I2 is A2 squared, so just 9 squareds. And then J12, if I work this out and plug in for these guys, what I find is it's 2 times square root I1, I2 cosine of delta phase change, phase difference. So in other words, this is the same as that for collinear propagation. So with the scalar model, I get the same thing as the electromagnetic model. So why would I ever use the electromagnetic model for collinear propagation cases?
Different polarizations.
Different polarizations. You have to use the electromagnetic model. What if I have the same polarization state? Scalar works great. Okay, so what we want to do now meaning Thursday, is we want to look at some sort of classic interference situations and apply these models to those situations and understand how they work and what they mean. And then for fun, we're gonna throw coherence in there and see how coherence affects things. And what you're gonna find is that it's not difficult to understand all of it based on the concepts we have and that you now understand so very well. Okay, so we'll see you on Thursday.